Okay, here we go. All right, this particular section is 18.1, temperature and heat. And what we're going to do is I'm just going to read through this. This is the BOV version. You can listen to this. Immediately following, you'll be answering some questions about 18.1. Here we go. Temperature and heat. After we read this, you should be able to explain the relationship between temperature and thermal energy. And you also should be able to define heat and specific heat. Introduction. The hot air and sand in Death Valley, which is a desert, which is in the desert, have a lot of thermal energy or kinetic energy of moving particles. But even cold objects may have some thermal energy. That's because the particles of all matter are in constant random motion. If cold as well as hot objects have moving particles, what, if anything, does temperature have to do with thermal energy? It's a good question. Temperature. No doubt you already have a good idea of what temperature is. You might define it as as how hot or cold something feels. In physics, temperature is defined as the average kinetic energy of the particles in an object. We just say hot or cold. When particles move more quickly, temperature is higher and an object feels warmer. When particles move more slowly, temperature is lower and it feels less, and the object feels cooler, less hot. Temperature and thermal energy. Pardon me. If two objects have the same mass, the object with a higher temperature has greater thermal energy. More mass, higher temperature, greater thermal energy. Temperature affects thermal energy, but temperature isn't the same thing as thermal energy. That's because an object's mass also affects its thermal energy. The examples in the figure below make this clear. In the figure, the particles of cocoa are moving faster than the particles of bath water. Therefore, the cocoa has a higher temperature. However, the bath water has more thermal energy because there is so much more of it. It has many more moving particles. Bill Nye the Science Guy cleverly discusses these at this address. So what we're going to do is we're going to take a look at this video right now.
Science guy. The mountains are icy, but they've got motion of molecules. Ha! See, even cold things have heat. Things like snow and icy mountain lakes and glaciers. They've got heat. Anything with molecules has heat. It's just that the molecules in cold things are moving more slowly than the molecules in warm things. You with me? Okay, y'all ready? Sing along. It doesn't matter whether something feels cold or hot. If molecules are moving, heat's something all things got. You know the words now, sing along. It doesn't matter whether something feels cold or hot. Here's a question. Which has more heat energy? This hot burning match or this beautiful ice sculpture of science? Well, the match is hot, right? The sculpture's cold. Well, they're both made of molecules, right? But which has more molecules? Well, the ice sculpture. A lot more molecules. So although they're much colder than the match, they actually have more heat energy. More molecules, more heat energy. Think of it this way. Suppose you tried to take a burning match and use it to melt the whole ice sculpture. Well, it's not going to happen, right? I mean, the match is going to run out of molecules long before the sculpture. So, more molecules, more heat energy. Ooh, ow, ow! Careful. We broke this one. Bill Nye the Science Guy.
All right, very good. So we're going to press on. If you're still not clear about the relationship between temperature and thermal energy, watch the animation temperature at this URL. So let's go ahead and click that. Wow, look at this. This is quite a bit of information. You can refer back to it, but in this particular web page, they talk about temperature versus heat, measuring temperature, the transmission of heat by conduction or conductors versus insulators, transmission of heat by convection, convection in the troposphere or convection in the asthenosphere, which is one of the layers of Earth, and transmission of heat by radiation, which is by the sun. Here we have some very important readings in terms of measurement, measuring the amount of heat in something. We have both. We have all three Kelvin, Celsius, and Fahrenheit scales. You can refer back to these pictures concerning temperature or heat. Let's move backwards. All right. So here we are. Alright, so here we have the cocos at 60 degrees Celsius, 140 degrees Fahrenheit. And then bath water at 39 degrees Celsius and 102 degrees Fahrenheit. Which one had more thermal energy? Well, the bathtub has more water, so it has more mass. Therefore, it has more thermal energy, even though the cocoa's hotter. Measuring temperature. Temperature is measured with a thermometer. A thermometer shows how hot or cold something is relative to two reference temperatures, usually the freezing and boiling points of water. Scientists often use the Celsius scale for temperature. On this scale, the freezing point of water is 0 degrees and the boiling point of water is 100. To learn more about the measuring of temperature, watch the animation measuring temperature. You can go back to that and take a look at that yourself. More often than not, we don't use Celsius in terms of a temperature measuring scale. We are very accustomed to the Fahrenheit scale. That's all of our weather measurements in North America typically revolve around that Fahrenheit. Did you ever wonder how a thermometer works? Look at the thermometer in the figure below. Particles of the red liquid have greater energy when they are warmer, so they move more and spread apart. This causes the liquid to expand and rise higher in the glass tube. Like the liquid in a thermometer, most types of matter expand to some degree when they get warmer. Gases usually expand the most when they're heated, followed by liquids. Solids generally expand the least, but they will expand if they are hot. Water is an exception, which takes up more space when it's solid than it is a liquid, and that occurs when water turns to ice, which is cold. Heat. Something that has a high temperature is said to be hot. Does temperature measure heat? Is heat just another word for thermal energy? The answer to both questions is no. Heat is the transfer of thermal energy between objects that have different temperatures. Thermal energy always moves from an object with a higher temperature, hotter, to an object with a lower temperature, colder. So it always goes hot to cold. When thermal energy is transferred in this way, the warm object becomes cooler and the cool object becomes warmer. Sooner or later, both objects will have the same temperature. Only then does the transfer of thermal energy end. You can scroll down and take a look at temperature versus heat if you like to by clicking right here. Example of thermal energy transfer. Here we go. The figure below illustrates an example of thermal energy transfer. Before the spoon was put into the steaming hot coffee, it was cool to the touch. Once in the coffee, the spoon heated up quickly. The fast-moving particles of the coffee transferred some of their energy to the slower-moving particles of the spoon. spoon particles started moving faster and became warmer, causing the temperature of the spoon to rise. Because the coffee particles lost some of their kinetic energy to the spoon particles, the coffee particles started to move more slowly. This caused the temperature of the coffee to fall. It got colder. Before long, the coffee and the spoon were at the same temperature. Back in the old days, in order to make something cooler, they would just simply put a metal utensil in it. And as a result, that metal utensil would draw away some of the heat, because heat energy always travels from hot to cold. So if you have something that's super hot and you put something that's room temperature, that's metal, in that, the metal object or utensil will absorb the heat, or some of the heat, from the mass of the very hot substance. Specific heat. The girls in the figure below are having fun at the beach. It's a warm, sunny day, and sand feels hot underneath their bare hands and feet. The water, in contrast, feels much cooler. Why does sand get so hot while the water does not? The answer has to do with specific heat. Specific heat is the amount of energy in joules needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Specific heat is a property that is specific to a given type of matter. The table below lists the specific heat of 4 different substances. Metals such as iron have relatively low specific heat. It doesn't take much energy to raise their temperature. That's why a metal spoon heats up quickly when placed in hot coffee. Sand also has a relatively low specific heat, whereas water has a very high specific heat. It takes a lot more energy to increase the temperature of water than sand. This explains why the sand on the beach gets hot while the water stays cool. Differences in the specific heat of water and land also affect climate. And if you want to learn more about that, you can click on this. Right here, the specific heat hammocks Earth Science Department. You can take a look at this. It'll give you more information on those 4 different types of matter and their specific heat. In the table below, how much greater is the specific heat of water than sand? Well, you take 4.18 minus 0.67, that's going to give us our answer. The KQED bridge thermometer. The roadway across the Golden Gate Bridge rises and falls as much as 16 feet depending on the temperature. Remember when I was talking about the bus? As the fog rolls in, the cables contract and the bridge goes up. Curators from the Outdoor Exploratorium in San Francisco have set up a scope 2 miles away so you can see how the bridge is moving up or down depending on the weather. So let's take a look.
A KQED HD production.
I'm Sean Lonnie from the Exploratorium. I'm the curator of Outdoor Works, and we're here at Upper Fort Mason looking at the Golden Gate Bridge. It's a wonderful view. We built this exhibit based on a question. We knew that something as big as the Golden Gate Bridge must expand when it gets warm. We knew it must move in some way, but we weren't sure how. So we chased that question down by actually instrumenting the bridge. We put a GPS locator on the middle of the bridge and cross-indexed that with 6 other units. So we had a very accurate reading up and down on the bridge, and we correlated that data that we collected, the up and down, with the temperature rising and falling with a NOAA weather station just on the other side of the bridge. So we had weather, and we had the temperature, and we had wind speed. And so what we found was this wonderful dance. As the temperature rose during the day, the bridge started to sag. And then as the temperature dropped off as the sun set, the bridge picked back up. And so what was driving that was something called thermal expansion. As the metals get warm, they expand. So those long cables that hold up the bridge deck, they expand and get longer, and the bridge sags. So one of the unexpected things we found was there's actually a 2-hour delay between the temperature rising and the bridge sagging, because the bridge is such a big thing, it takes that long for the temperature to affect the metal and the metal to sag. So we built this scope so that you can see that. So if you come by on a warm day, you look through this scope and you see the bridge and you see the traffic moving. And we have a reticle here, little lines on the screen. And you can see whether or not it's below or above average. So if it's a hot day, you can come by and expect the bridge to be as much as 11 feet down. The total excursion is 16 feet, total engineered. So it can be low as that or as high as 5 feet, depending on the temperature, depending on the load of the bridge. As the temperature goes up and down, the bridge goes up and down. And it essentially turns the bridge into a very slow, massive thermometer.
All right, well, that's pretty interesting. So in summary, temperature is the average kinetic energy of particles of an object. Warmer objects have faster particles and higher temperatures. If two objects have the same mass, the object with the higher temperature has greater thermal energy. Temperature is measured with a thermometer. Likewise, if you have two objects of different sizes, the one that has more mass will have greater thermal energy. Going to the next one. Heat is the transfer of thermal energy between objects that have different temperatures. Thermal energy always moves from an object with a higher temperature to an object with a lower temperature. Specific heat is the amount of energy in joules needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Substances differ in their specific heat. Now what you're going to do is you're going to take this information and you're going to use it to answer some questions. On your particular website where you have 18.1 temperature and heat, you will notice in this area there's a orange button that says practice. If you would please go ahead and do that practice session. Make sure that you earn 100%.